I'm just going to read some of this. So Blade is a library which provides a secure and distributed message brokering system with support for custom protocols based on RPCs and event channels, while also providing protocol directory services, node presence, and identity mapping services. So in essence, what this does is nodes on the network, so we'll get into terminology in a minute, but every machine that's connected or every handle of the library that's created, it effectively creates a node on the network. Now, node presence is something that's obviously important to a lot of people. You got to know when nodes come online and offline. And protocols in specific. Now, protocols, these are basically a sub-layer within Blade. So if Blade was like the main protocol, within Blade there's the ability to execute sub-protocols. Now, Blade keeps track of that sub-protocol directory and allows you to locate those protocols anywhere in the network once they're connected. So if you're providing a number of different services, they could be OpenSIP's proxy into FreeSWITCH territory. They could be small devices, embedded MQTT type things. Anything like that, you would have a node that you talk to, and that node is communicating for you or connecting you to the network. So Blade can be embedded into existing services to enable communications and integrations, building on industry standards like TLS, WebSockets, and JSON RPC. So a big reason for the why is because a lot of these other protocols that are out there, they're not really utilizing the existing technology that we have available to us, particularly things like RTC with the web coming along now. We wanted to utilize more of that. We wanted to take advantage of WebSockets, the ability to communicate directly into Blade from the web and not have to deal with these complicated proprietary protocols. By using JSON RPC, we work with something that's already fairly well known, and extending that system allows people to get into using Blade a lot easier from different languages. We do intend to support, I believe, at least a JavaScript version. Tony can probably answer how many different languages will follow down on the Blade client line, but you will always have the complete C library as well. So some of the features that Blade supports. Well, it's based on a tree network topology to start with, which allows us to have a central master node that's actually sitting at the center of the network. This central master node acts as the authority for a number of different things, including event channels and as a protocol directory. It's the one who handles maintaining all of that information. Now, a master node can run like any other node as part of an existing service to utilize the existing hardware that you already have there, but we recommend to probably run it as its own standalone system. We've called that Switchblade. And basically all it does then is sits as the master and manages all of the network communication that goes through and allows it to run very efficiently without any other white box code going on in the background that could cause problems. Okay, so the next thing that we looked at was the ability to support multiple transports. We do have a default transport based on WebSockets and TLS and actually built off of the libks WebSockets that have already been used for other things. But the idea behind this default transport is that it's going to support everything that you need to. If, however, you want to communicate into the Blade network using other protocols, for example, trying to manipulate something like MQTT to directly talk to it, you could do something like that. It would take a little bit of effort, but it is possible. And then you could have this kind of proxy system that the transport basically converts MQTT to Blade for you. The next thing we looked at was realm segregation, and the idea behind this is to support logical subnetworks of different nodes. Nodes in the network are going to probably work together, and quite often only a few of those nodes will be communicating with each other. Coming back to the example with Bogdan, OpenSIPs, right? It's going to be sitting in it could be participating in multiple different realms. On one side, it could be exposing access for those Verto clients or whatever are communicating through Blade, and ultimately talking to SIPs. And behind that have a second realm, which is just for itself and the different FreeSWITCH systems that it's accessing and communicating. So what this allows you to do is create, exactly like it suggests, is a group or a subnetwork of nodes that are mostly for the purpose of creating isolation for sensitive information and stuff like that. Then we started looking at identity mapping. Now, identity mapping is a very complex subject. There's a big slide that's going to come up related just to that. But to briefly touch on it, the idea is to support virtual identities that'll always route back to the same node. So let's say you have, for example, a Leaf server that's actually servicing Virto. So on one side of it, it's accepting Virto connections in, and on the other side, it's talking to Blade. Well, that Virto server could potentially create virtual identities for each of those users that are connecting in, and those users are now routable directly back to that node. Doesn't matter where in the network you access that identity, it will always refer to communicating to that node, and that node can then translate the identity in the last mile to Virto communications. This is assuming that Virto wasn't built directly with Blade in mind. There's a lot of other uses for virtual identities as well. We extend this concept into the idea of like conferences. So when FreeSwitch creates a conference, it has the ability to create a virtual identity related to that conference, and then you can route messages to and from that conference, which ultimately goes to that FreeSwitch node. However, when it reaches the FreeSwitch node, it knows which conference based on the identity. Okay, now another big part of it is embedded RPC communications, and I briefly talked about this. Deep down inside of Blade, there is a message called blade.execute, and this is what effectively takes information from the protocols that have been published and allows you to execute that RPC across the network. It's a unicast type message, so there's a request out and a response back. The protocol is primarily in control of most of what data will be included, but there is some information in there for Blade routing, and we'll get into that shortly. Automatic routing and presence awareness. The idea here, basically, as soon as you register to the network, you're automatically known by a node ID, which is similar to an identity, except that the node ID is always routable without having to register anything specifically. Where identities are related to a specific realm, the node ID is something that exists for every node regardless of what realms they're participating in. Presence awareness, kind of covered that already a little bit. Okay, and then the other big piece of Blade is event channels. Now this comes down to a lot of what AMQP and other systems like that basically achieve. This is the main brokering of a pub sub type system, where you have the ability to create event channels and broadcast events to those channels, but you also have the ability to authorize people to subscribe to those channels so that you have control over it. And rather than thinking of it as broadcasting, it's actually multicasting, because the subscription system is what actually dictates who gets sent the message. So it's not just broadcasted over the whole system. It will only end up passing through the nodes that require it. All right, so there's some other features. We'll cover those at the end. All right, so some terminology. I'm not going to get too deep into this. I'm sure everybody can read. I'll just quickly touch on each of them. Nodes, we kind of talked about. So node is any physical system that creates a library handle. Master node is that master that's at the center of everything. The master kind of knows everything about the network, handles the core services. The router nodes are any nodes which accept downstream connections. So, for example, a master node is also a router node. But any node can be a router node if it chooses to accept connections and route messages for them. Messages, single frame of communication, represents a request, a response, or an error. That includes events and everything else. Routing, the process that happens when a node first registers or an event subscription is requested to be subscribed to. Basically, it just sets up routing information so that every node knows how it's going to reach any other node if it exists in the system. Transport, underlying system takes a message and transmits it over the wire. Connection is the bridge between transports and sessions. Sessions are the core context for most communications in the system. Of note, they're viewed as both upstream and downstream, just depending on the context in which you're looking at them. So for example, a master only has downstream connections, but everybody else always has an upstream connection. Upstream connections always lead to the master. Realms, kind of covered that. Logical groupings of identities and protocols, which usually operate together to provide a common task or function. Small networks are likely only to operate with a single realm. So if you only have, half a dozen or maybe 10 different systems in your network and you're only exposing 2 or 3 different protocols, you very well may only use a single realm. Identity, a universal human-friendly string identifier, allowing nodes to provide presence for resources and actors that are not directly connected to the Blade network as nodes. Now, that's not their only purpose, but that is their primary purpose. Protocols, the container which tracks information about custom published protocols, including controllers and channels. Fairly simple, we kind of covered those already. Controller, any node which actively provides access to a protocol. So if it publishes a protocol, it's a controller. Protocols can have multiple controllers, but most often are going to be exclusive to one controller, unless you want the system to round robin access. Channels, the container which groups multiple different events together. So a single channel can actually accept multiple different types of events. You can use this as a way to send a variety of different events, but on the same channel with the same permissions. Enables broadcasting events to channel subscribers. And presence, the concept of event channels related to propagating events when a node or identity begins or ends participation either in the entire network or a specific realm. So whenever a node enters the network, whenever a node leaves the network, whenever a node creates an identity as part of a realm, whenever it leaves the realm, all of those things are going to be part of the presence system. You'll be able to be notified of those things so that your protocol can be kept up to date as a controller, or you can find protocols, that sort of thing. All right, so here's what the tree network topology looks like. Basically, we have the master node sitting up there at the root. And I don't like to use the word tree. This is more like a river. It continuously splits into 1, 2 or more, depending on how many nodes are connected to it. But ultimately, as many depths as you want, just like a river, and we say upstream in order to get back to the master. So some benefits of this, every node can potentially be a router for more downstream nodes. As you see here, service node 1 over here is actually serving to route for 3 and 4. Nodes can rely on a single upstream session to predictably reach the master authority. So depending on how far your depth down is, you always know exactly how much effort it's going to take to reach the master node and back. This helps you in defining your own network topology, so that if you want to create clusters of nodes that are connected to a specific node because it communicates to that node a lot, that's not a bad idea. For example, you might have the OpenSIPs controller being the router for a bunch of FreeSwitch nodes. This way, the FreeSwitch nodes and the OpenSIPs are constantly communicating with each other and generally don't have to leave that little section of the network. The master node is all-knowing about the network nodes and provides a directory to locate protocols exposed by services within a network. So any one of these nodes could publish a service. When it does, master node knows and can let any other node that asks for it how to reach it. It allows for complex service deployments, including proxy-like protocol controllers, which can intelligently direct traffic to clusters of service nodes. This is something we've already talked about. The ability for, say, service node 1 here to be OpenSIPs and 3 and 4 to be FreeSwitch boxes. Any node can be routed to by only knowing the node's ID, which are randomly generated GUIDs. So these will be randomly generated every time you connect to the network, but you can alias additional human-friendly identities. So if for some reason this service node here is actually a controller, not just a router, you might want to give it a friendly name just to make it easier to access. Okay, supports native least cost routing for most messages, such as protocol RPC executions and broadcasted events. So let's say that service node 4 here is trying to communicate with, say, service node 3 over here who's published a protocol. After it's located that protocol, it only needs to bounce through service node 1 and then down to service node 3 to communicate. It does not need to bounce all the way up to master. It does not need to cross more nodes than it is required to pass in order to reach that destination. This can be very useful again in network topology layout. It allows you to have some control simply by where you connect your nodes. It can be huge on network efficiency. There's a high degree of horizontal scalability, allowing nodes of service clusters to communicate with each other as well as other services. So again, coming back to the idea of having a bunch of free switch servers running in one realm, you can continuously add more to that realm and just have it automatically become part of the cluster, have it communicating with the controller. Basically, it just starts up with configuration and away it goes. And it can automatically basically become part of that cluster of free switch servers that are all supported by one controller. Master nodes as well as router nodes can be embedded into an existing service or operate as light standalone services to scale throughput. So the master node, service node 1, service node 2, these could be just switchblade services running connected to each other. These would allow for a higher degree of throughput if you need to create more scalable network. And of course, you could create, 10 of these things connected to the master node and distribute your scale as you needed to. The transport system is pretty important. It's basically all of the data delivery under the system. So I'm just going to quickly read through this. The transport system provides a mechanism by which a connection can be established and can send and receive messages. The messages use JSON for the format, while the transport code is abstracted. This allows additional transports to be implemented while still supporting the core RPCs, which implement the blade functionality in a universal way. This abstraction can allow other ways to access into a blade network, but the default transport should be sufficient for most needs. Transports provide the underlying data movement for a connection, but also produce connections. Connections provide the universal bridge between a transport implementation and a session. Sessions provide the context for communications with upstream or downstream nodes and are created or recovered by the transport during the connection state machine startup. A connection will exist without a session for a short period until completing the blade.connect process. Meanwhile, a session may exist without a connection for a short period, which has a TTL and represents the time when a session may be recovered if the connection was briefly lost. Now that's a bit of a mouthful right there, but basically what that's saying is that connections need to exist for a little bit while we get the ball rolling. But more importantly, if a connection is lost, there's a short period of time when that connection can reconnect and reestablish the same session without having to negotiate or have to go through any of the routing processes again. So if it had 10 or 15 nodes downstream from it, it wouldn't have to go through and reestablish all those connections again. Which is really handy because we know networks aren't always reliable. In most cases, these are going to be running on some sort of intranet or local area network, but even those have hiccups too. The default transport implementation used by Blade is built upon secure WebSockets. In normal operation, the transport will only operate with TLS-enabled connections. This ensures that there's some security. It can also act in a router capacity by providing a listener thread to establish downstream connections, which is enabled if the required configuration is provided to specify the IPs and ports. Pretty basic. Since the support for TLS is in the default transport is mandatory, identity information from the client certificates may propagate into automatic identity mappings during the initial Blade Connect process to an upstream router. Now, we've already talked about identity mapping a little bit, but the idea is that since we're going to be using TLS, clients will be issued certificates in order to connect to the network. That's part of the trust process. And part of that process is that we could pull information out of the certificate to automatically register identities into the network for them. Now, since identities are required to be are required to have a realm, there's still some work to be worked out there. But conceptually, identities could be somewhat automated. All right, so transport requirements. Transports must be reliable and sequential in the data delivery, like TCP. Transports must provide connection-oriented properties, such as keep alive and connection loss detection, again, like TCP provides. Transports must provide TLS or equivalent negotiations and encryption as the first layer of security in Blade, such as our WSS default transport does. Transports must provide a callback for creating outbound connections to another node for upstream connections. This is mandatory at a very minimum so that you can create an upstream connection using a transport. Transports must provide callbacks to send and receive messages and to handle the state machine states for the connection. And transports must handle the first blade.connect message during state machine startup state to establish a connection, or a session for the connection, which includes lingering session recovery. That last one's again a mouthful, but basically at the very end of the transport kind of setup process, you process this blade.connect message and you set up the session, whether that's recovering it or creating a new session. All right, so then we get into realm segregation. Again, the next couple of slides are a little bit of thick text, but okay. Realms provide a means to create a logical grouping of identities and protocols within the Blade network. Identity mappings are always created in the context of a realm, and similarly, protocols are always published within the context of a realm. This can be used to create subnets of protocols and identities. However, a node is not formally participating in a realm unless it maps at least one identity using the realm. New realms can be registered on the fly and may require a mechanism for authorizing access to permit mapping identities and/or publish protocols using the realm. Realms can provide another layer of encryption, which allows for message parameters that are not required for routing to be additionally encrypted with a realm level key. Basically, that allows for an additional level of encryption at the realm level in case you are creating a larger network and you don't want certain parts of that network to be exposed to other parts. You can kind of hide the critical details. This additional layer of encryption would allow actually black boxing segregation where an identity mapping must have been accepted to obtain the realm level key, and therefore only those with the key can actually understand any sensitive data within the messages. One example use case for multiple realms could be to hide a cluster of FreeSWITCH servers within their own realm, each publishing as a controller to a protocol in that realm and only processing requests when they are from identity mappings in the same realm. The FreeSWITCH servers could communicate with each other in the same realm through RPC calls and event channels. However, it is also possible another separate protocol and controller could exist within that realm to coordinate distribution to the FS servers while also participating in it with a different identity mapping in a different realm and protocol to effectively create a cluster load balancer for the FS servers. This comes back to what we were talking about with Bogdan's OpenServe stuff. This example even goes so far as to showing how one could recognize a request to a conference which already exists on one of the FS servers in the cluster and be able to direct new participants to the correct server already hosting the conference. But there are many potential use cases for realm segregations which will depend on individual integration needs. In many small Blade networks, it is likely you will never need more than a single shared default realm, and that will be the target for default configuration out of the box for Blade. Okay. Last really thick one, I promise, guys. Identities provide an alias that leads back to a node for routing purposes, but enables a node to dynamically process the identity with respect to specific resource or context. Identities are in a standardized format utilizing URI-like structure with the format of entity at realm/resource. While the entity and realm portions are required, the resource portion is not. The realm portion is obvious and should match a permitted realm. The entity and resource portions are more open for the user to define as needed. This flexible structure ensures that identities map to the right node but leave the processing of an identity into the hands of the end user. However, the realm portion may be required for internal verifications. It is also possible that an identity mapping for an entire wildcard of resources may be required. Registration of wildcard identities can be supported and would allow matching all identities within the wildcard pattern. For example, PSTN at FreeSWITCH/star would allow a node to register that any matching identity is routed to that node. For example, PSTN at FreeSWITCH/ a phone number would match and be routed to the node, which could then be parsed by the end user for further processing. One example of how this could be used is for a protocol which manages conferences on behalf of a cluster of FreeSWITCH servers. It may create an identity for each conference it is providing, such as conferences at FreeSWITCH/42. And as such, messages destined for the identity will route to the node, but the node is able to identify which realm and conference resource is backing the identity, in this case named 42. Another use case could be Virtual clients connecting to a Leaf node with a Virtual endpoint and Blade enabled. Each of the Virtual clients could be associated to a virtual identity on the network, such as Virtual at FreeSWITCH/sbuild. that is visible and routable. Messages destined for the client reach the node hosting the identity and can then be translated through the Virto endpoint to the associated client context for the last mile. Such a system would allow presence about each indirect Virto client to be announced to the Blade network through its identity and inform any services that are interested about its state, such as the previously mentioned conference example. In keeping with the above examples, if the Virto client was transmitting audio and then the notification for that client transmit status could be passed in an RPC message between Virto at FreeSwitch/Esprelt and conferences at FreeSwitch/42, allowing the conference to be notified that the specific participant of the conference is transmitting without influencing other conferences the client may be in as well. This is in spite of the fact the actual client is represented by an identity mapping, and the RPC message was actually generated by the Virto service hosting the Virto client on the Blade network. Likewise, the specific conference identity can be used to inform participants through their identity about the transmit status updates of other clients. Messages can still freely exchange using node IDs directly between real nodes, but these would imply direct communication with the node and not tied to a specific identity context or realm, and are primarily for internal message routing. However, a node can register identities for whatever purpose it may require, including a simple human-friendly alias to use in place of the node ID if desired within the default public realm. Okay, identity mappings are complicated. There's no way to get around that, but they also provide one of the most important aspects of the system. Hopefully, this gives you a bird's eye view on it. There's so much more that can be done with them and will be done with them, but if you can kind of grasp the core concept of how an identity allows you to give reference to a resource or an external connection or basically anything that you want to be able to refer back to the node with and have presence on the network, you're golden. All right, so then we get into some of the RPC communication. Then we get to see a few images. Yay! Okay. The Blade protocol is comprised of two different RPC layers. Most of the main functionality required to support internal operations for Blade are handled in the first layer, referred to as the core RPC layer. The Blade.connect core RPC message was mentioned earlier, which handles the initial session negotiations as well as providing initial network segregation realms and the master node ID. During this process, a Blade.register core RPC also occurs upstream, processed by every node along the path until reaching the master node. This provides the required internal information for a routable path between the master node and any newly registered node on the network. The following illustration roughly shows the flow of the network traffic up to the session establishment using the default transport for a small branch of the earlier sample topology. So what we see here is basically we have our master node over on the right, and we're only looking at the nodes that are connected down the left. And we have our transport negotiations that occur, and we have a Blade connect that occurs. And because that service node 1 is only connected to master node, there's no more Blade.register that happens. However, because service node 3 is actually connected through service node 1 as a router, it goes through its transport negotiations, and it does its Blade connect just like it did before. Except, service node 1, upon receiving this, will send a Blade register up to master node saying, if you want to find service node 3, use me to get there. The master node is aware of node 0001 directly connected to it, and is also aware that it can reach 3 using node 1 as the immediate downstream router to reach it. Any level of depth is supported. The core RPC layer has so far provided session establishment and node registration, but some additional core RPCs exist to support the embedded RPC layer called the protocol RPC layer. Protocols are defined within the context of a realm and are both published and located through core RPCs, which communicate directly to the master node using Blade.publish and Blade.locate, respectively. Router nodes between only relay and do not process these core RPC messages. When a protocol is published, the publishing node becomes a controller for the protocol. Protocols may be exclusive and support only a single controller, or may support multiple controllers in a round-robin type configuration. Protocols can also be located through the master node by requesting the protocol name for a specific realm. So here again we see basically what happens is, using the same nodes, service node 1 decides that it's going to publish a protocol, so it talks to master node and it lets it know that it's going to publish a specific protocol. And then at some point later, service node 3 decides that, hey, I want to know how to find this protocol, who's providing it. So it does a blade.locate. The fact that it does not stop at service node 1 shows that it is simply proxied through it and routed. It doesn't actually stop here and get processed. It goes straight to the master node, goes back, gets the information, and says, hey, you can find that protocol on service node 1. From then on, any communication would directly be between 3 and 1 without going to 0. So after this exchange, node 3 is aware that it can execute protocol RPCs for the given protocol using node 1 as a control. As part of the blade locate, an implicit special channel subscription might exist to allow propagation of updated controller information, such as if a protocol becomes unavailable or an unavailable controller is added or removed. This would ensure that when locating a protocol, internally the node retains a cache of protocol location details that can be used for future protocol RPC executions, but would also require a way to unsubscribe when no longer interested in receiving locate cache synchronization events. Alternatively, every node could be kept updated about all protocol changes to avoid locating protocols on demand. Otherwise, for the moment, you just call locate and hope to hell it works. Okay, protocol RPC methods are executed through an embedded execution core RPC. To call a protocol RPC, the blade.execute message is used. Similar to the core RPC layer, it follows much the same internal data structure, however, includes protocol-specific fields in addition to important fields for internal routing purposes. It is also worth noting that blade.publish and blade.locate use the same internal routing fields for direct relaying to the master node. So as we saw before, whenever you see a line that goes straight through a node, it's suggesting that it has the ability to route without actually communicating to that node on the way. When executing protocol RPC methods, the routing occurs for both the request and response messages by following the path that is most direct. By nature of the routing tables, a node always knows if another node can be located downstream from it, or whether the message should travel upstream instead. The following illustration continues from the prior examples and shows that node 3 executing a protocol RPC method using node 1 as the controller. So as we said before, this blade execute would have passed through all the way to whichever node, but since we're actually connected to it from 3 to 1, we're able to communicate strictly between the two without going further out on the network. As node 3 directly connects through node 1, it is using it as a router. The routing begins and ends between these two nodes when a protocol RPC execute occurs between them. Fairly efficient, least cost routing. Wow, I guess I have a couple more thick ones. As we've seen already, when a new node connects to the network, its node ID is registered to create a path between the new node and the master. Every node along the path becomes aware of the node's presence and which downstream session can be used when routing messages to that node. When a session terminates between two nodes without a graceful termination, the upstream node will let the session linger for a short period, allowing the original node to reconnect and recover the session. When this occurs, any messages destined to the lingering session in the meantime will be queued until a reconnect occurs or the session times out. If a session is reconnected before it expires, then all existing routing information related to that node and downstream nodes routed through it remains intact. That's important. However, if a session times out or gracefully disconnects, then all routing information related to that node and any downstream nodes routed through it are cleared from the system by way of propagating additional blade.register commands to remove the relevant node presence from the network. When a session is terminated, in addition to the routing information being removed, any protocol controllers and protocol event subscriptions related to the node are also purged from the network along the path up to the master. It will also be possible to opt into an event channel about node's presence. This will allow a node to obtain node presence updates as they occur. For example, a node which provides a conference protocol would need to track the network presence of conference participants. And when one of those participants suddenly goes offline, it needs to be notified to remove them from the participants. Presence events may also extend to Presence events may also extend to nodes joining the network. However, it is very likely that nodes joining and leaving realms with identity mappings being added or removed also require event updates to notify about identity mappings. As with the conference example, an identity that represents the conference itself may exist, and there may be nodes out there which wish to know when the conference identity is no longer available, such as a media load balancer, which decides where to send someone. Okay, events are complicated. So we're just going to try to skim through it here, but the explanation on the picture should give a little more information. The event channels represent one of the most important concepts within Blade. The system provides the ability to broadcast messages and have them received by nodes without sending the message to every node individually. To support this, we revisit the Blade.publish core RPC, but also introduce a few new core RPCs, including Blade.authorize, Blade.subscribe, and Blade.broadcast. When a protocol is published, and then also dynamically after that, event channels can be added to and removed from protocols. For example, to create an event channel related to a specific conference when the conference has started, and to remove the event channel when the conference no longer has participants. When a protocol controller has created an event channel, the controller will call to Blade.authorize, which will contact the master node and update an event channel to permit a specific node ID or identity mapping to subscribe to the event channel. If an event channel is public, then no authorization is required to subscribe. However, whether public or authorized, when a node or identity wants to receive events for a channel, they call to Blade subscribe, where the node contacts the master to verify the authorization, and on a permitted response from the master, all nodes along the path will create the extended subscription routing information back down the path to the subscribing node. This is important because this ensures that the master is given the opportunity to authorize before any of the subscription paths are created, so that we don't have to clean them up if it fails. This took a little bit of work because this is not like other ones where a lot of the stuff happens on the request path. This actually happens on the response path. When a node on the network, most likely the protocol controller, wants to produce an event to a specific event channel, it can do so by a call to Blade.broadcast. This message will travel from the node producing the event in an outward pattern. First, by checking if the node producing the event is a router with downstream nodes. If so, then checking if any downstream nodes are subscribed, and sending the event message to the session, which will reach the subscribers. Then, the node producing the event will also send the event message to its upstream router node. Events always propagate upstream to the master node to ensure all branches that may contain subscriptions can receive the event. An event message will never travel back through a session it was received on, therefore avoiding events traveling in circles or being received by any node more than once. So this is a little example of kind of the process that happens. So the first thing that happens here is service node 1 is publishing a protocol. Master node is updated about it. And during this publish, it's created a channel, an event channel. Then service node 2 over on the right, on a different side of the tree, it does some sort of Blade execute that ultimately causes the controller of the protocol to require authorization, or more importantly, to provide authorization for that node to the event channel. In response to receiving the Blade.execute response from the original controller, it will include whatever channels you were authorized for. So this is a little bit misleading in the sense that this first Blade.authorize is actually happening at the same time as the Blade.execute. Before the response for the Blade.execute is sent back, the Blade.authorize is completed to inform us that, yeah, that was okay. And in the Blade.execute, we include those channels that are now permitted. Finally, service node 2 does a Blade.subscribe saying, yep, I want to subscribe to that channel. It contacts the master node, and that process effectively gets it subscribed. Well, actually, it subscribes up the path, and as explained, subscribes it. Now, over here, service node 3 does more or less the same thing. Just showing this in order to show the difference of what's happening. Here, it does a Blade execute to service node 1 without having to relay. Then, same Blade authorize occurs to the master node. Finally, the service node 3 subscribes to that channel. Here we see it actually jumping multiple steps all the way up to the master node, being processed every step along the way in order to add the subscription information on the response. And finally, we have a blade.broadcast, which occurs, and doesn't really matter where it occurs from. The simple fact is that it gets propagated to everywhere, and ultimately service node 2 and service node 3 end up receiving it because they're subscriptions. And this brings us to the conclusion, where there's just a couple of other features. Probably didn't fill this in with everything, obviously, but there are a number of other features that are not worth significant details. A few of those features are listed here. Configuration can be generated at runtime and fed into the library without being loaded from a disk file. So they're kind of similar to using curl or the like to do dial plans on FreeSWITch. All memory related to the current sessions, routing tables, extended subscription details, identities, and other runtime data should be shadowed into a file, either an unQLite database or something like that, or synced live with another offline node that can be used to provide high availability IP-based failover strategies, allowing one node to recover sessions as an HA backup failover for another node that has a hardware failure. This is of particular importance to the master node, as it's currently a single point of failure, but it will also require protocol directory failover and require keeping all the details intact for downstream sessions to reconnect without reestablishing the sessions across the entire network. Now, for those of you who haven't fallen asleep, appreciate your patience, and hopefully that was informative about Blade. Any questions?
Shane, from my perspective, I think it was a great walking through the Blade, for people coming from outside without too much of a, let's say, in details knowledge of, all the things in Blade. So thank you for putting this together.
Oh, that's my pleasure. I'm glad it wasn't too thick and you guys didn't fall asleep through some of the
No, actually, if you could, if it's okay to share the slides, maybe, for more lecturing later.
Yeah, absolutely. I will probably continue to update this over time and try not to make it too thick, keep it in the 15 slide range, but I do think that there's probably going to be a few more details that could fit in there over time.
Okay.
Brian's laughing. I'm sure there's
Kathleen asked me something. She asked me, and I was laughing at what she said.
Oh,